This is Daniel Coosbury, and we're going to keep looking at some basic fundamental probability rules. Now, you have to pardon, my voice is still kind of not there, so pardon the occasional cough. You may want to turn up your volume if I'm not coming through very loud enough. But in this particular video, we're going to look at what's called the addition rule. Now, the addition rule is something we want to use for a certain kind of compound event. So I'll show you the definition of a compound event first. A compound event is an event that is formed by combining two or more events. So imagine we have an event A or event B. There are two different events we're talking about. And one kind of way of combining those events into a compound event is to say A or B. Like, what's the probability that A or B happens rather than just one or the other? So this is what we mean by compound. We got two different events going on. And this is a special kind. It has the word or here. So we need to get our heads around what we mean in probability when we say the word or. So the event A or B occurs whenever A occurs, so that's one thing that could happen, or B occurs, or A and B occurs. So or the word or suggests it's either this one or that one or both of them. All three of these could happen, and we still have the event A or B occurring. So that's what we mean by A or B. This is a special kind of compound event. I'll show you another one in another video, but specifically we're looking just at the A or B. So when we start talking about A or B, one thing or another thing happening, we're going to need to use what's called the general addition rule. So the general addition rule is something you use when you're doing the probability of A or B. And the formula looks like this. The probability that A or B happens is equal to the probability that A happens all by itself, the probability that B happens all by itself, minus the probability that they both happen. So this is a formula that you're going to use a lot when you're doing compound events using the word or. Now, this little Venn diagram is supposed to kind of help us understand what this formula really means. So imagine that this left circle is the event A, and this right circle's the event B, and we want to describe what's happening when we talk about A or B. So A or B means that either A can occur, which means anything in this left circle could occur, or B could occur, and let me use a different color for that one. Let's let B be the blue one. B could occur, which means anything in this right circle could happen. And if we just simply take the probability of A, which is this left circle, and add it to the probability of B, which is this circle, we're considering if A happens or if B happens. What actually happens is we double shade this middle section. So there's a little middle section here. That might not be very helpful. Let me take that away. But you see, I've shaded it with both red and blue. So if these events can occur at the same time, if I just add A to B, I've actually counted this middle part twice, which this middle part is A and B and B. That's what this middle part's talking about. So if I just add these things together, I've counted the A and B part twice, which I don't want to count them twice. Double counting is bad. So that's why this little part at the end is helpful. When you add A and B together, you double count the middle part, and so subtracting one of those will end up just counting that part once. So if you subtract it once, then you end up just counting the middle part once and not double counting it. So that, anyway, I don't know if that makes a lot of sense, but that's where the formula comes from, and this is just a formula you're going to use anytime you see the word or. So let me show you an example. This is a quality control example. You're producing some sort of item, and you want to make sure that they all work, and you're kind of analyzing defects. So this is a new computer off an assembly line, and among a sample of 100 units, 3 of them fail to boot up properly because of a defect in the motherboard. I'm going to refer to those as the motherboard defects. 4 units had a hard drive failure, so I'm going to call that a hard drive defect. Oh, no. I don't know what's going on there. There we go. And 2 units experienced both failures, so both their motherboard and their hard drive defected. So we want to use this sample data to find the probability that either type of failure occurs in the next computer you sample. So this is an example of using sample data to compute a probability. So what I really want to see is I want to find the probability that we have either a motherboard failure, that's motherboard, or a hard drive failure. So if either one fails, the computer breaks, and so I want to use or, like this one or that one. Both of them are bad, so I'm going to use the or. And using the addition rule on the last slide, this is the probability that the motherboard fails, plus the probability that the hard drive fails minus the probability that they both fail. I'm just going to be lazy and write both. That's motherboard and hard drive. Sorry, I'm changing technology a little bit and trying to get my handwriting better, and it's not really working. But this is what we're doing. Find the probability that the motherboard fails, the probability that the hard drive fails, and then subtract the probability that both of them fail. And we can use this data to do that. So the probability that the motherboard fails, 3 of them failed because of the motherboard. That's going to be 3 out of 100, because 3 of them failed just because of the motherboard. The probability that the hard drive fails is 4 over 100, and that's just coming from the paragraph up there. And then the probability that both of them fail is going to be 2 over 100. And then when you do that addition and subtraction, you end up with 5 over 100, which ends up being 0.05, which is that on the borderline for being unusual. But this is the probability that the next, using this data, this is the probability that the next computer you get ends up failing for one reason or another one. And that's using the addition rule, because it is possible that both of these failures happen at the same time, and it looks like it did here. So that's the probability that the next computer you get is going to fail. Now, based on your management, your protocols or whatever, this is the kind of number that you want to be as small as possible when you're producing things. You want as few defects as possible, and so if you think that anything 0.05 or less is acceptable, then this is acceptable. If you want it even higher quality, then this may be unacceptable, but this is going to be a helpful number, and we use the addition rule to find it. Now let me show you, there's another part of the addition rule that we need to look at, and before we need to understand what a mutually exclusive events are. So the addition rule is going to change for mutually exclusive events. Mutually exclusive events are events for which it's impossible for both of them to occur at the same time. In other words, either one's going to occur or the other one's going to occur. On the last example, the hard drive defect and the motherboard defects were not mutually exclusive because they could both happen. And in fact, both of them did happen on a few of them. So they're not mutually exclusive. Let's see if we can see if any of these are mutually exclusive. A die is rolled. Event A is that the die comes up a 3. Event B is that the die comes up an even number. And the question is, are these mutually exclusive or not? Well, can a die end up being a 3 and an even number at the same time? The answer is no. So these are mutually exclusive. You get that? So it can't be this and that. It's got to be one or the other. So they're mutually exclusive. Here we have a fair coin being tossed twice. Event A is that one of the tosses is heads. I forgot to write exclusive here. One of the tosses is heads, and event B is one of the tosses is tails. Now, is it possible to toss a coin twice and get 1 heads and get 1 tails? It is. So since both of these could happen, these are not mutually exclusive. It's possible for both of these to occur. Just like the hard drive and the motherboard failure, it's possible for them to both occur. But this is one where they're mutually exclusive because you can't roll a 3 with a die and it also be an even number because 3 is an odd number. You can't have it both ways. So let's look at the addition rule for mutually exclusive events. If A and B are mutually exclusive, then the probability that they both occur is 0. And that just comes from the definition. Like they can't both happen at the same time. So the probability that they both happen at the same time is 0. It's impossible. So 0. And so because of that, the addition rule changes a little bit because now you don't have an and part that you're subtracting over here. It's just 0, so we just leave it out. So for mutually exclusive events, the probability that A happens or B happens is just the probability of A plus the probability of B. So if this is A, this is B. I just put this on here. There's no intersection anymore. There's no middle part to subtract because there's no A and B. So this is a much simpler rule. So if we can determine that events are mutually exclusive, our work becomes easier because we just add 2 probabilities together. That's kind of nice. So here's an example. In a recent year of the Olympic Games, a total of 11,544 athletes participated. Of these, 554 represented the United States, 314 represented Canada, and 125 represented Mexico. What is the probability that an Olympic athlete chosen at random represents the United States or Canada? So we want to find out the probability that the athlete is from the U.S. is representing the US or Canada. Now, the first thing we should do is ask ourselves, are these mutually exclusive events? Is it possible for an athlete to represent the United States and Canada at the same time? And it's not. Now, you may be thinking, well, they could be from the US and from Canada at the same time, but I think the Olympic rules say you've got to pick a team. You can only represent one country at a time. So the probability that you have an athlete who's from the US and that's representing the US and representing Canada at the same time has to be 0. They're mutually exclusive, which means we're going to use the simpler addition rule for mutually exclusive events. We're just going to find the probability that they're representing the US plus the probability that they're representing Canada. And there's no and part to subtract this time. So the probability that they're representing the US is 554 over the total number. The probability they're representing Canada is 314 over the total number. I'm going to do that adding real quick. So you see, this is a much simpler rule to work with. We don't have any sort of technicalities because we determined ahead of time that the events were mutually exclusive. So I just did that in my calculator, and I got 0.0752. I like doing probabilities to 4 decimal places, rounded to 4. So this is the chance that you get someone who's representing either the U.S. or Canada. So the addition rule with mutually exclusive events is nice, and if you can determine they're mutually exclusive before you do any calculating, you could make your life easier because there's no and part to subtract. Okay, here's one more example, and I wanted to do one more just because when you're working through things, you've got to make the decision whether or not events are mutually exclusive so that you do the addition rule well. And even if you don't, you just might make work harder for yourself. So deciding that events can't occur at the same time can be really helpful going forward. So here we have 1,000 adults who are asked whether they favored a law that would provide support for higher education. In addition, each person was classified as likely to vote or not likely to vote based on whether they voted in the last election. What is the probability that a randomly selected adult is likely to favor the law? So we want to find out. I'm sorry, I didn't finish reading. Likely to favor to, let me say that again. What's the probability that a randomly selected adult is likely to vote or favors the law? I'm sorry, there are 2 events there, and they're joined by the word or, just like everything else in this video. So they're likely to vote or they favor the law. Okay, so the first question we need to ask is, are these mutually exclusive? Is it possible that you're likely to vote and you favor the law? Well, yes. In fact, there's a whole bunch of people right here that are both likely to vote and they favor the law. So it is possible. They're not mutually exclusive, which means we need to use the addition rule, just the general addition rule, to find this. So we're going to do the probability that you're likely to vote or, I did that right, or favor the law, likely or favor, which is the probability that you're likely plus the probability that you favor it minus the probability of both happening at the same time. So we got to find all 3 of these things. The good thing is the both one is already right here. So the probability you're both likely to vote and you favor it is 372 over the total 1,000. So now we got to find the probability that you're likely to vote and the probability that you favor the law. So the probability you're likely to vote is going to be the total number of people in this likely to vote row. So all of these people are likely to vote. So I need to start by adding those 3 numbers together, which is 372 plus 262 plus 87. When I do that, I get 721 over 1,000. And that's me just taking the probability of that you're likely to vote. All these are likely to vote. So that sum is going to be 721. And then I want to find the probability that you favor the law, which, let's see, that these people favor the law and these people favor the law. So we're talking about the 2 numbers in this column that favor the law. So I'm going to add those 2 together now, the 372 plus 151. And I get 523 over 1,000. So that's the probability that you favor the law. So that's this thing right here. And this is this thing, if you're following along. And if you're following along, you may have noticed that in the calculator, I've added 372 both to that number, and I added 372 to that number, which means I added it twice, which is why we got to take away the 372 over 1,000. This is where the addition rule really comes into play. Is I added it twice already when I was computing the red number and the green number. And so I'm taking it away because that's what the addition rule tells me to do. I counted it twice. So because these events weren't mutually exclusive, I had to use the addition rule the long way. And then I'm going to add the red number to the green number and then subtract the blue number. And I get 872 over 1,000, which ends up being 0.872. And there's nothing to round. That's the exact number there. So this is the probability that you're either likely to vote or you favor the law. So it's another example of one where I had to do it using the addition rule, the general addition rule, and subtracting that middle part. So your takeaways from this is that you use the addition rule when you're doing this or that. So look for the word or. And deciding if things are mutually exclusive or not is going to help you with the calculation. Because if they are not mutually exclusive, you got to do the long thing. If they are mutually exclusive, then you're just adding the two probabilities together. You're not subtracting the and part. And that's how you do problems like this.